The amount of reaction force a support member can generate to oppose a load is called the strength of the support. The strength of the load-bearing member depends on two factors. 1. The material from which the object is constructed, and 2. The area of the load-bearing member the load acts on. The greater the area, the greater the load it can support. So for a given material, the amount of load a material can withstand per square meter is a constant for that material. For engineers to determine the load a support object can withstand, they need to know the area on which the load acts. Stress is defined as the load acting on the member divided by the area on which the load acts. If we know the strength of the material and the area the load acts on, using the above formula we can calculate the safe load a member can safely support. For the stress formula above, the load will be in force units, kilonewtons, meganewtons, and giganewtons, but the stressed area must be in square meters. So if the load was 1 meganewton and the stressed area 1 meter squared, then the stress would be 1 meganewton / meter squared, which is 1 MPa, or megapascals, the same unit as pressure. Example: a pillar has a cross-sectional diameter of 500 millimeters and supports a load of 1,000 kilonewtons. What is the stress on the pillar? As we can see, the stressed area is the circular area of the top of the pillar, having a diameter of 500 millimeters. Step 1. Find the stressed area. The diameter of the pillar is 500 millimeters or 0.5 meters. The stressed area is the area of a circle, which is 0.54 times d squared, where d is the diameter of the circle. Plugging the numbers in the formula and doing the math, we get a stressed area of 0.196 meters squared. Step 2. Find the stress on the pillar. Stress is load divided by area. So stress is 1,000 kilonewtons divided by 0.196 meters squared, and the stress comes out to 5093 kilopascals. Note, since force was in kilonewtons, stress will be in kPa. We will be dealing with three common types of stress: tensile stress, compressive stress, and shear stress. When an external force acts on a load-bearing structure and tends to stress the object, it is called tensile stress. A cable suspended from a beam with a heavy load attached is subjected to tensile stress. Example: a 500 kilogram wrecking ball is hanging from a cable that has a 1.5 centimeter diameter. Neglecting the weight of the cable, what is the stress in the cable? Okay, so step 1, we have to change the mass of the wrecking ball to weight or load. So weight equals mass times the constant 9.81 meters per second squared, and the weight comes out to 4905 newtons. Step 2, find the stressed area. The diameter of the cable is 1.5 centimeters or 0.015 meters. Because the cable's cross-sectional area is a circle, we can use the formula for a circle to find the stressed area. Doing the math, we find the stressed area is 0.0001767 meters squared. Step 3. Find the tensile stress. Stress is load divided by area. So the stress is 4,905 newtons divided by 0.0001767 meters squared, and the stress comes out to 27,758,913 pascals, or 27.8 megapascals. Our second type of stress is compressive stress. Compressive stress acts along the axis of an object towards its center and tends to shorten the object. A pillar is subjected to compressive stress. Example: 2 columns support the weight of a bridge and a truck equally. If the truck has a mass of 2 tons and the bridge a mass of 1.5 tons, what is the stress on each column if the diameter of each column is 0.8 meters? Step 1. Find the total mass of the truck and the bridge. Total mass equals the mass of the truck plus mass of the bridge. Total mass equals 2 tons plus 1.5 tons. Total mass equals 3.5 tons. Step 2. Changing mass to weight. Total load, or weight, equals the total mass times G. Total load works out to 34.335 kilonewtons. Step 3. Find the load on one pillar. Load on one pillar equals the total load divided by the number of pillars. Load on one pillar is 34.335 kilonewtons divided by 2. Load on one pillar equals 17.1675 kilonewtons. Step 4. Find the stressed area of one pillar. Stressed area of one pillar equals the area of the circular cross-sectional area of the pillar. Stressed area of one circle, 0.7854 times the diameter of the circle, which is 0.8 meters. Stressed area of one pillar equals 0.502 meters squared. Step 5. Finding the stress on one pillar. The stress on one pillar equals the load on one pillar divided by the stressed area of one pillar. Stressed area of one pillar equals 17.1675 kilonewtons divided by 0.502 meters squared. Stressed area on one pillar equals 34.15 kPa. Because the load is in kilonewtons, the stress is in kPa. While both tensile and compressive stress act along the axis of the loaded member to lengthen or shorten it, shear stress acts perpendicular to the member to shear or cut it in two. Example: the footbridge shown is supported by 2 horizontal joists and 4 vertical pillars. Each pillar is attached to the end of a joist by a horizontal bolt having a diameter of 2.5 centimeters. The load acts down to try and shear the bolts, causing shear stress. If the load is distributed evenly, then the load on each bolt is 1/4 the total load, and the stress is reduced accordingly. If the total load is 4,000 newtons, what is the stress in each bolt? Step 1. Find the load on each bolt. The load on each bolt equals the total load divided by the number of bolts. Load on each bolt equals 4,000 newtons divided by 4. Load on each bolt equals 1,000 newtons. Step 2. Find the stressed area of each bolt. Diameter of bolts 2.5 centimeters or 0.025 meters. Stressed area is the area of a circle. The stressed area of one bolt is 0.00049 meters squared. Step 3. Find the shear stress in each bolt. Shear stress on each bolt equals the load of each bolt divided by the stressed area of a bolt. Shear stress on each bolt equals 1,000 newtons divided by 0.00049 meters squared. So the shear stress on each bolt equals 2,037,178.5 pascals or 2.04 megapascals.